Here we are at example 1 from our 3.8 number 2 set of notes. Now we're told that a 10-foot ladder is leaning against the side of a building. And the top of this ladder is actually sliding down at a rate of 2 feet per second. So it's actually going downwards 2 feet every 1 second. And because it's going downward, what we're going to do is actually throw that negative in there, because again, that height is going down. So it's negative 2 feet every 1 second. How fast is the bottom of the ladder sliding away from the wall? So as we can see, this ladder is sliding down 2 feet per second. Then it's also sliding out at some rate as well. That rate we do not know, but it's sliding outwards 2 feet per second. And because it's sliding outwards 2 feet per second as opposed to towards the wall, that change in x is actually increasing there, because again, x is getting larger, as you can see from the diagram. Y is getting smaller, but x is getting larger. And as a result, our dx, our change in x over the change in time, we don't yet know. That's what we're trying to figure out. Again, that's the change in x over the change in time. These are the same thing. And we're kind of given another piece of information to kind of help us out, and that is the fact that what is this rate when we know that y is 8 feet off the ground? So y is equal to 8 feet at that specific moment. We have no idea what is x, we have no idea what is the change in x over the change in time, but luckily we have some things to help us out with in terms of the y's, like the changes in the y over time and y. So right now, what we can do is we notice that this is a ladder against the wall. It forms this perfect right triangle. And if you recall back to geometry, Pythagorean theorem is pretty nice to know. We have x squared, so our leg squared plus our other leg squared equals our hypotenuse squared, plus y squared equals our hypotenuse squared. So in this case, we'll call them, well, we know what our hypotenuse is, it's just 10 squared. And if we just simplify this up a little bit, we end up then with x squared plus y squared is equal to 100. And at this point, we notice that we have two variables, two unknowns. Well, if we think about the situation, we have a ladder. This hypotenuse is always 10. The ladder is not actually changing in terms of height. Okay, the ladder is always literally 10. But we notice that the height over time, in other words, this y, is changing over time. You know, it's going downwards. Likewise, the change in x, or in other words, how many feet per second is this ladder moving outward, is also changing all the time. Now, as a result, you actually have two variables changing over time. Now, if we go back with related rates from the first section, what we did was we took everything and put them in terms of just one variable. And let's go ahead and just explore what happens when we try and do that. Well, if we're trying to find out what is x, let's get things in terms of x. So in other words, we want this y squared to be stuff in terms of x. So if we were to take our Pythagorean theorem, x squared plus y squared equals 100, we would end up then with, or actually we can even go back to this, it doesn't really matter, but we would end up with y squared is equal to 100 minus x squared. And then if you take the square root of both sides, you'd end up with y is equal to plus or minus the square root of 100 minus x squared. And so if you go ahead and substitute that back in for y, we end up then with x squared plus, it doesn't really matter with the plus minus, because when you square it, it's going to be positive anyway, but when you throw this in there, And if you already know what's going to happen, please bear with me. I'm just kind of showing the y. We have x squared. What would happen here, again, this is really irrelevant because it's going to be squared. There's this square root would cancel with the squared, leaving you with plus 100 minus x squared equals 100. Well, x squared minus x squared is gone. 100 equals 100. Well, yeah, I mean, it does. And this step might really sound trivial because what we've done is we've just taken an equation, solved for a variable, resubstituted it back in to itself, which of course it should produce a true statement. I mean, that should happen. But the reason why I really wanted to show you that was because even when you try and solve for a variable here, there's not much that we can do. I mean, all you really end up here is a true statement. So as a result, we maybe have to take another strategy. And again, going back to the diagram, we notice that the changes in y's are happening. This thing's going downwards. Likewise, the change in x over time is also happening. And so now the predicament becomes, well, what happens if you have two variables changing over time? When we were talking about like the oil spill examples, usually we just had like a radius that we had to worry about. Or we could express like the height in terms of radius. Well, now it's much more difficult to express x and y together when they're actually two separate kind of things going on. Now, at least though, we have some information though that can help us out. We'll talk about that in a moment. But if you recall back to implicit differentiation, it says that we can take the derivative with respect to whatever we want on both sides. In this case, we're always taking, with related rates, we're always taking the derivative with respect to t. So let's at least go ahead and try and do that. Well, again, here is an outside function and an inside function. So this just becomes 2x dx over dt. So again, the outside function, rewrite the inside function, take the derivative of the inside function. Plus, the same exact thing is actually going to happen for y. We're going to take the derivative of y squared, so that comes out to be 2y. Derivative then of the inside is just dy over dt. Luckily, the derivative of the right side just comes out to be 0. I mean, derivative of any constant is just 0. So again, what we've done there is we've taken the derivative with respect to t on both sides. At this point, what we can do is go ahead and substitute in what we know and what we are trying to find. So at this point, we know that our dy over dt is negative 2 feet per second. So that's this guy. So we have negative 2 feet for every 1 second. We also know our y. It's 8 feet specifically at that time. And again, that's being multiplied by 2. Now, we have no clue what our change in x over change in time is. That's actually what we're really trying to find. We also don't even know really what x is. Right now, he's just x. But we can use something to help us in finding out what is x. Well, if we think about this triangle, we have our hypotenuse. We also have a leg at the exact moment that we're looking for, 8 feet. Well, all you have to really use is Pythagorean theorem to figure out what is that other leg. In this case, we end up then with x squared plus 8 squared equals 10 squared. So, in just doing a little bit of side math, we end up then with x squared plus 64 is equal to 100. Solving for x from here, we end up with x squared is equal to 36. So x comes out to be 6. In this case, we are talking about feet. We're going to omit the negative just because you can't have negative distance for this wall, or this length. So we're going to go ahead then and throw in that 6 feet in for x. And when we do that, we end up then with 2 times 6 feet. No clue what our change in the x over change in time is. It's something. Plus, I'm going to go ahead and clean this up a little bit. We notice that we end up with 2 times 8 times negative 2. That's going to give us negative 32 feet for every 1 second is equal to 0. So I'm just going to clean this up a little bit more. We end up then with 12 feet dx over dt minus, I just realized this is actually going to be 32 feet squared. Again, because feet times feet. So minus 32 feet squared every 1 second is equal to 0. And then we're just pretty much trying to solve for our dx over dt. So we would do that by adding this piece over. So we end up then with 12 feet dx over dt is equal to 32 feet squared for every 1 second. Then we're going to divide both sides by this 12 feet. So dx over dt comes out to be 32 feet squared for every 1 second. Again, really you'd be dividing this fraction divided by this fraction, but what I'm going to do is just multiply this first top fraction by this reciprocal on the bottom. So when we do that, we have times 1 over 12 feet. And as a result, then we do see one of the feet end up canceling out. And that should really happen because if you think about it, we are trying to figure out how fast is this change in x going outwards. Well, it's not going to be feet squared because it's not an area. It's just the length that it's moving outwards. And just kind of simplifying this up a little bit more, looks like our change in x over the change in time comes out to be 8/3 feet per second. So again, though, that is example 1 from our 3.8 number 2 set of notes.